Okay, so let's start the lecture. We're going to start the topic on optimal control, but today we're trying to review is on the concept of a mean, max, and constrained optimization. Okay, and then we'll go into the optimal control, which is actually where we're going to have this linear quadratic optimal control. Okay, yeah. So first, the concept of mean and max. Mean and max is a concept you get into when you're in the first year, basically. So the first mean and max, so let's talk about unconstrained. Okay? Unconstrained problem, basically. What this is essentially is from very simple situation. If I have a single variable, okay, single variable function, and you probably ask is what is the maximum value and what is the minimum value does this function have over a certain range, right? So, and what is the minimum or maximum of y over x belong to a certain range? Okay, yeah. And what you do is, if you recall that, what do? You basically first derivative test. So y prime or df over dx and set it to 0, right? So basically the function maybe behaves like this, or maybe it's this. Okay, yeah. So you look at the slope. When the slope is 0, so you reach the minimum or maximum, right? Yeah. But slope is 0 doesn't tell you. It only tells you the location where the minimum maximum is, but it doesn't tell you whether it's a minimum or maximum. So the first derivative test give you so-called critical points. Okay, so-called critical points. And what we need is we need to do a second derivative test. To give us the information whether it's a maximum or a minimum, right? Yeah. Second derivative test. This is basically can be derived from Taylor series. If I have a function f of x, and this function f of x can be expanded using Taylor series, expand that function over certain value of a, basically at x equal to a. The Taylor series of that function is f of a plus f prime of a, x minus a here, and f double prime of a over 2, x minus a squared, and then plus all the high order terms, right? Plus all the high order terms. So when you do the first derivative test and you set equal to 0, basically if x of a is a critical point, okay? If x equal to a is critical, and sometimes we also call that stationary point, okay? If this is a critical point, then this term is gone, right? This term is gone. Okay? And this term is gone, which means f of x minus f of a, okay, fx minus f of a is approximately f double prime a over 2 x minus a squared at here. So ignore the high order term. Okay? Yeah. So x minus a squared is guaranteed to be greater than 0. Then here you have two situations. We're talking about the second derivative test. So basically this guy here. If f double prime a is greater than 0, okay, if this guy is greater than 0, so what do you think this x of a is? Do you think it is a minimum point or maximum point? That's right. It's a minimum point, right? Because it's greater than 0, basically any change around the point x equal to a end up with a positive value. Can you see that? So if this is x of a here, then any change around this x equal to a here, then that minus that is guaranteed to be greater than that value, right? So x of a is a minimum. And if f double prime is less than 0, then x of a is maximum. Now, we said it's minimum or it's maximum. More precisely, okay, it could be a minimum. We should call that local minimum or local maximum, okay? Because your curve, maybe it's looking like this. So basically, if we have minimum here, and this is the local minimum, this is the local minimum, but within this range, and this is a global minimum here. Okay, so that's the concept here, right? So what happens if this guy is 0? If it's 0, then we actually can't determine that, so we have to do a higher order test, third order test, right? Yeah. Okay, so that's the first order. That's function of a single variable. Okay, function single variable. So it's a function of two variables. Okay, function two variables. You can do similar process at here. You can do basically do a Taylor series for function of two variables. Okay, so let me write down the Taylor series function of two variables here. If you do this one here, let's see, at x naught, y naught point, the Taylor series is f of x, y, and equal to f of x naught, y naught, okay, plus fx, okay, x minus x naught. Well, maybe I should let's write this. Let's see. This is partial f over partial x at here. Okay, and plus partial f over partial y at here. Then plus 1/2. Okay, partial f over partial x squared, x minus x naught squared, plus partial f Okay, so that's a Taylor series for function of two variables. Okay, for function of two variables. Okay, now in order to check, okay, before we move on here, for function of two variables, okay, the first thing that you need to establish the concept is when you plot this thing here, it's a surface. Okay, basically it's a any kind of surface that would be, and this is a, why could I call this y here? It's a z, right? Okay, it's a z here, z equal to f of xy. So if you plot it, it's a surface. Okay? Just in general, maybe it's a surface like this. Okay? Or maybe it's something more complicated surface, right? Yeah. Then where would that be? Basically, where would be the minimum point or maximum point for the surface, right? For the surface. So there's a concept you learn in 248, okay, the engineering analysis 3. The concept is called gradient. If you recall that, you learned a concept called gradient. So what is a gradient? Gradient is if you have a function f at here, then the gradient of this function f is what? It's this, right? It's this. Okay, it's this. The geometrical meaning of a gradient. Okay, geometrical meaning of gradient is, this is a vector, first of all. Okay, so gradient of the function f give you a vector. And this is a vector in the xy plane, right? In the xy plane. The geometrical meaning of gradient is, it's a vector which points to the direction of the greatest increase of the function f of xy. Okay, so this gradient f, this gradient here, it's a vector. Okay, points to the direction of greatest increase of function f of xy. Okay, yeah. So what does this mean basically? So this is the vector here, right? If you draw this vector in xy plane, basically at any point here you can draw a vector. At this point you can draw another vector basically. Okay? And those vectors, you basically plug it in, you draw the vector. And what does that direction of the vector represent? That direction of the vector basically represent is the greatest increase, okay, of the function f of xy. So you go up there, okay, so that basically tells you, okay, what direction would you walk to, okay, what direction would you walk to such that this guy right here will have the greatest increase along this function there. Okay, so that's basically gradient function. So now you think about it, if I'm looking for is the minimum or maximum point of the surface, then basically means what? If you are already, if this location basically happened to be, if this location happened to be the minimum or maximum location here, so where would you walk to? You don't walk to anywhere, right? You don't walk to anywhere, basically, which means the gradient will be 0. Okay, so you look at this guy here, that's essentially the first derivative test, right, as to a function of the two variables. Okay, yeah, so this is your first derivative test. Okay, so first derivative test is to set, basically to set this del f equal to 0. Setting del f equal to 0 meaning you set df over dx is 0 and df over dy equal to 0. Okay, so solve the equation right here and then you can get these critical points, right? You can get the critical points or stationary points. So then you end up with certain set of critical points. Okay, yeah. Okay, but the critical points doesn't tell you whether you are at the minimum location or maximum location here, right? So then you need to do a second derivative test. Okay, second derivative test. So what's the second derivative test then for the function of two variables? So this has to be, okay, explained or coming back to the Taylor series at here. Okay, Taylor series. So when you do the first derivative test and you set it to 0 and you find critical points. So let's say x0, y0 is your critical points. Then which means what? Which means this is at x equal to x0. This is basically at x0, y0 location and x0, y0 location. Okay, yeah. So this is basically the partial derivative here and here going to be 0 here, right? And then the difference is this guy minus that equal to what? Equal to this by neglecting the high order term. So if you look at this thing, those things set here, those are basically second derivative tests. Okay, second derivative test. And more precisely, those are at the critical points there. Okay, So basically substitute, okay, those values in there. All right. Yeah. Okay. So I don't want to go into too much of mathematics here. In practice, basically here there is this situation here. Maybe I should just mention this here. Okay. So you see, this is a function f of x, y here, and when you take this first derivative test, you end up with this, okay, df over dx, df over dy. As a matter of fact, this is called a Jacobian here. Okay, and when you do the second order derivative, so let's say this, if this is called j here, okay, if this is called j, and then when this is a j with respect to the variables x and y here, okay. So let's say if I call u as the variable x, y, so this is, let's call it gu, okay, as a first order. Then when you do the second derivative test, you're basically taking is second derivative of this, another derivative of this Jacobian here, okay, another derivative Jacobian. And this derivative Jacobian, you end up with the so-called Hertzen matrix here. And the Hertzen matrix is this. It's d square f over dx squared, and d square f over dx dy, and d square f over dy dx, and d square f over dy squared. Okay? See if that makes sense or not, right? You're taking the partial derivative of this guy with respect to x and y, okay? Right? So the first term here, take a partial derivative with respect to x, that becomes second order. Take a partial derivative with respect to y, and that's this one here, right? Yeah. So this is called a Hertzen matrix. Maybe double S. Okay. Now, in terms of the second derivative of test, so here's a theory. Okay, here's a theory here. Okay. This whole chunk at here. Okay. If you're interested, this whole chunk at here. Okay. This whole chunk at here can be rewritten. Okay, let's define this as a vector u at here. Okay, let's define this as a vector u, and let's define that u naught as x naught y naught here. Okay, and x naught y naught here. Then this whole chunk, this basically this part at here, is equivalent to, can be rewritten. Okay, so sorry about that, and I'll just write it here, and we can manage that. That equal to 1/2 u minus u naught transpose, and that Hertzen matrix GUU u minus u naught. Okay, it can be rewritten like this in a very compact form. Okay. So if you look at this one here, okay, look at this one here. Those are in vector formats. But however, okay, this is actually, in terms of formality, this is actually not much difference from first derivative like this. You know, some derivative x minus a bracket square. Okay, bracket square. So because of vector, so you don't have a square vector. Basically, here is this transpose times this. So in terms of this order, this is called a quadratic format. Okay, this is called a quadratic form. Okay, quadratic. So quadratic form is always this form. It's xt matrix A and x. This is a quadratic format. All right. Yeah. Quadratic is meaning second. It's order of 2. Right. So something to the power of 2. That's a quadratic. Okay. Yeah. Right. If you have 1/2 mv squared. Right, that's second order, but you can write it as v transpose mv. If it's a scalar, the same thing as this, right? Okay, that's called quadratic. So back in here, this quadratic here, second order derivative test basically is to look at what's the sign, right? What's the sign of this guy here? Is it greater than 0 or is it less than 0? However, okay, this one here, it's not simply just a greater than 0 because it is a matrix at here, right? Matrix at here. So what do we call that is, we don't call it greater than or less than 0. When it's a matrix at here, we call that whether it's a positive definite or negative definite. Have you learned this concept already? So positive definite basically means, so let's say A is positive definite if this X transpose A X is greater than 0 for any X not 0. X is a vector. Okay? For any X is not 0. And A is negative definite if X transpose AX is less than 0 for any X not 0. Okay? Yeah, that's negative definite. Then coming back here, the X naught Y naught would be a minimum point or maximum point determined by this positivity or negativities of this term at here. Okay, of this term. So if this is greater than 0, I'll put it simply, or if this is a positive definite, then the X naught Y naught would be a mean point or maximum point. It's a mean point, right? Yeah. So if this basically if this term at here okay is PD positive definite, X naught Y naught is a mean point. And if this thing is negative, okay, definite, then this X naught Y naught is a maximum, okay, location, okay, maximum location. If this guy is either positive definite or negative definite, then we can't determine that. We have to do a higher test, okay, like that. In the lecture notes, I have given you a different version of this theorem here, but it's basically similar ideas here, okay? Similar ideas. So the bottom line is basically when you have a function, okay, maybe it's a single variable, function of 2 variable, or maybe it's a function of 3 or 4 or even more variables, all right? But it's always the same thing. It's always basically do first derivative test and then the second derivative test. Okay? Yeah. So that's how you end up. That's how you get your mean and max. And this is what we call unconstrained, okay, optimization. Okay, unconstrained. So then it comes to the second one here, which is a more general situation. That's basically what we call constrained optimization. Okay, and here I'm gonna introduce a concept. Basically, we are looking at the concept called, okay, Lagrange, okay, multiplier. Okay, Lagrange multiplier. Okay, and how do we deal with this constraint and optimization and here? So here's the here's the setup of the problem here. Okay, here's the setup problem. I'll use function of two variables as an example. So what you want to do is, maybe you want to do is, I want to maximize or maybe minimize, okay, a function z equal to f of x, y. So if I just say minimize or maximize this function here, that's basically the unconstrained problem, right? Unconstrained problem. Okay, what we just said there. Now this time we add a constraint. So suppose that it's subjected to a certain constraint. Let's call the constraint as this. So g of x, y equal to c. Okay. So this is our constraint at here. All right. This is our constraint. So what does that mean here? Basically, if I draw a diagram, okay, this is probably your function, okay, z equal to f of x, y at here. So you're trying to basically minimize or maximize the function. In this case, probably finding minimum or max minimum here, right? Subject to this g of x, y equal to c. So if I plot g of x, y equal to c, what would that be? That's basically a curve inside the xy plane, right? Inside xy plane. So basically, the question here is, you are constrained to the locations on this curve at here. Okay? Imagine that you are walking along this curve here. Okay, you're walking along here, and ask yourself, at which location along the curve is the minimum or maximum from this surface at here? That make sense? Okay, so that's constraint problem here. So for example, when you're walking here, okay, you're probably at this location. And you're walking here, and you're probably at this location. When you're walking here, you're probably this. You're walking on here, you're probably at here, right? So that's probably is a minimum location at here. So that's basically how you find it, right? Okay. So how do we find this problem here now, right? How do we basically deal with this constraint problem? I'll give you a simple example. So there are many practical examples in terms of a constraint problem here. So let's say, for example, suppose that you are trying to construct a fence. Okay, you're trying to construct a fence here. Now, construct a rectangular fence. Okay. The length of each side, let's say, is W and L. Okay. And what you know is the W and L. You know the cost. So the cost, okay, the cost for those blue colored, for these three sides at here, okay, for those three sides, and is, let's say, is a $30 per meter. Okay, $30 per meter. And the cost for the red side here, which is on one side, right? For the one red side, is $50 per meter. Okay, yeah. So then you know that your total cost, right? Your total cost is going to be how much? Three blue side is $30 per meter. So how many W? I have a 1W, 2W there, and a 1L. So L is 50. So $50 times L plus how much? 2W. Yeah. So 6W, 60W here, right? 2 by W by 30. In a second here.
Isn't there 2 W sides and 1 L side on top? So shouldn't it be 2W plus L times?
Yeah, 2 by W by 30, right?
Plus L.
Hmm?
1 L is blue.
Yeah, 1 L is blue. This L here.
Yeah.
The blue side is $50 per meter, so this is a 50 times L.
I thought that was red. Red is 50.
No, these three sides are blue sides.
Yeah.
Cost you $30 per meter.
Yeah, so total length shouldn't be 2W plus L?
Yeah, $2 plus L. Sorry, yes. What I'm looking at, so yes, sorry about that. Yeah, $30 by L plus 60W here, right?
Plus
yeah.
50.
Plus 50? Oh yeah, we haven't finished yet, right? Yeah, plus 50L. So overall, it's 80L by 60W. Okay, so that's your total cost. And you're basically trying to minimize this cost at here, right? Minimize this cost. So that's an unconstrained problem if nothing else is added. Now, if somebody's saying, okay, you're not just minimize the cost at here, I'm going to add a constraint. So we're trying to minimize the cost subject to a constraint here. What's the constraint? Subject to, let's say, constrain yourself to the total area. So this is your land. You can be more than 1,200 meter square. Okay, so that's your constraint, right? So basically, this one in here is our function, the z equal to f of x, y, right? As I was giving you at here. And this one at here is that g of x, y equal to a c at here. Okay. Yeah. So how do we solve this kind of a constraint optimization problem? For simple ones like this, okay, you can basically algebraically trying to solve this one here. For example, so what do we need to do? I can basically, here's WL equal to 1,200 meter square. So let's say then I can get W equal to 1,200 divided by L, right? Divided by L. Then substitute this quantity over here, right? Over here. So you get your C becomes 80L plus 60, 1,200 over L, right? Over L here. Okay? So then overall, this is how much? 80L square plus a certain number at here over L at here, right? Over L. So what are we doing? We're trying to minimize this whole thing here. So basically, this is a quadratic function, and you're trying to find the minimum point for the L, right? Yeah. So take first derivative. This is a single variable now, right? Take the first derivative, second derivative, find the minimum. Okay. So that's when we are doing it here. Okay. When we're doing it, but in our case, let's look at more general situation. Okay, more general situation, and basically we're gonna look at this from this diagram at here. So let me redraw that. Redraw the diagram there. So we're gonna use the gradient concept, okay, to illustrate this situation here. So here is a function f of x, y. Here is the constraint of this, right? There's a constraint of this. Okay. Yeah. Now let's think about one simple case. Okay, think of a simple case study here, maybe. So let me redraw one more head here. So let's say if your walking direction is, okay, if your change is always this line, it's a straight line at here. Okay, let's say it's a straight line. If this is a straight line at here, and this is the surface at here, as you are walking along the straight line at here, Basically, when you're walking here, the corresponding point on the surface is here. When you're walking here, the corresponding point on the surface is here. So what would you expect after you trace out the points on the surface as you were going along this direction here? What would that be? It's parabola, right? It's basically you end up with the intersection between this plane and this surface here. So that's the intersected curve, right? Synthetic curve. Okay. Then now here comes the question now, right? Here comes the question. You're walking along this direction. Let's say I'm going to call this direction as u hat. Okay, is u hat. You're using unit vector to represent the direction of the walking here. When you're walking along the direction, you trace out a curve at here. Okay, trace out a curve. If I call this is your positive displacement direction, positive s. Okay, positive s. So the question here is, where would be the 0 point? The 0 point always represent is what? Is a derivative is a 0, right? I mean the minimum point here is a derivative of 0 here. So if it's a single variable, here, how did you find this point here? You actually, the idea is you are actually walking in the positive direction of x here. This is your u hat. You're basically walking in this direction here, right? And then you take df over dx. So x is a positive displacement direction. You set equal to 0. Make sense? So here you same idea. Where is my positive direction? It's not x or y anymore. It's s, right? It's the positive s. So what would you do? You take a df over ds. Okay, ds. In which direction? In the u hat direction, right? So remember, what do we call this? It's called directional derivative. Okay, it's called directional derivative. So where is the mean point or maximum point? And that's when what? That's when the directional derivative equal to 0. That's right. So equal to 0 gives mean or max. Okay, gives mean or max. What is the directional derivative then? Directional derivative has a formula. Directional derivative equal del f dot u hat. Okay. Directional derivative equal del f dot u hat. So if the directional derivative is 0, so if this guy is 0, this is a vector, this is a vector. Dot product of two vectors equal to 0 means that's right. The two vectors are perpendicular to each other, right? So that basically means the del f is perpendicular to u hat, okay, to u hat. So at this location, suppose that this is the location of a mean point here, okay? This is the location mean point. Then at this location, your u hat is still this direction. Then the del f probably is that direction, right? Okay. Or maybe in this case, in my drawing here is actually this direction. Okay, it's this direction. Okay. Is that okay? Yeah. This is very important. Okay. So just understand this concept here. At the minimum point, your del f needs to be perpendicular to the u hat at here. So now coming back here, now my walking line is not a straight line. Okay, it's not a straight line. It's a curve, but I can always use a tangent vector. Right? I can always use a tangent vector, which is tangent to this curve or the constraint, as what? As the direction of walking, right? Or direction of displacement. That make sense? Okay? Yeah. So, as you're walking along here, it's not going to just trace out a flat parabola here. It's probably going to be a curve, right, with up and downs like this. Okay? Yeah. However, it's the same idea. At a certain location, if you reach the minimum of that point or maximum, the directional derivative, right, is still going to be 0. Okay, it's still going to be 0. At the 0, your del f is still going to be perpendicular to the u hat. Okay, so here's the point here now. So at the critical point, the del f perpendicular to u hat. Okay, del f is perpendicular to u hat. And what is u hat? As we said, u hat is defined as this tangent vector to the g, to the constraint at here. Okay, to the constraint. What about the del g then? Right? If I take grading vector g, del g, there's a one sentence I wrote here is when we talk about the gradient is the direction, points to the direction of greatest increase of that function, okay, of the function here. So there is this rule here. The gradient of the function g is perpendicular to its tangent vector u hat, okay, to tangent vector u hat. So del g is guaranteed to be perpendicular to the u hat. So now let's think about this situation in here. You have, let's say maybe I'm right at this location here. Okay, this is your minimum. Okay, this is your minimum. At this location, this is your u hat, and we know that at this location, your del f is perpendicular to that, and at any location along curve, your del g is also perpendicular to that, right? Also perpendicular. So tell me, what's the relationship between del f and the del g? Parallel. So that means del f must be parallel to del g. And that's the condition at critical point or stationary point. Make sense? Right? And what is del f? What is del g? They're basically two vectors. When two vectors are parallel to each other, that means what? They must, So del f parallel to del g. That means the two vectors must be just the difference of two vectors parallel each other. They must be just the difference of what? First, what's the same? If the two vectors parallel each other, they must be pointing to the same direction. But in terms of magnitude, which is what? Just the difference of scale, right? Just a different scale. Okay? So, all of the talking at here, okay, for a constraint optimization, essentially it's this box at here, okay, this box. How do I know where the critical point is, right? At the critical point, right, what is satisfied? This guy here, okay, this guy. This is the relationship. Okay, this is the relationship at the critical points. Okay, at the critical points. So, can you use a positive? Yes, you can. Okay, so you can absolutely use a positive here. So I use a negative. Basically, the reason is I can just basically rewrite that like this. Okay, like this. The lambda at here is called Lagrange multiplier. Okay, it's called Lagrange multiplier. So just simply based on this expression in here, if you just simply look at this expression in here, and what we have is, remember what a del f is, right? Del f is a vector. So del f is a vector df over dx and df over dy. Okay, df over dy. So then, looking at this this relationship here, we have basically df over dx plus lambda dg over dx equal to 0. And the other one, df over dy plus lambda dg over dy equal to 0. All right? Yeah, that's what we get. So, let me show you an animation in here, okay? And let's look at just a second here. Maybe let me finish the writing in here, and then we'll look at an example, and then I'll show you the animation here. Okay? Yeah. So then the next thing here is this. You have this condition derived. Okay, you have this condition derived, and this is what you need to satisfy in order to find this critical points. So bear in mind, we do have another one here, right? Which is what? The constraint. Okay, we do need also have this one in here. So there's one very neat way to combine this all together in one function in here. Okay, in one function. So here's what you do, and let's basically consider this is number one is this del f equal to negative lambda del g. And number two is this constraint in here. Okay, that's the constraint. Then we can combine that. Well, let's define ourselves an L equal f of xy, okay, plus lambda g of xy minus c. Let's define ourselves a new function. L equal to f of xy plus lambda multiplied by g of xy minus c. Okay? Yeah. This function is called Lagrange function. Okay? So this is called the Lagrange function, or simply can call it Lagrangian. Okay? So you can call it Lagrangian here. In mechanics, there are two very famous ways of doing formulation. One is called Lagrangian. The other is called Hamiltonian. Okay, so this is actually a fundamental concept of so-called Lagrangian kind of formulation. All right. Yeah. So this function is Lagrangian here. Right. Now, let's think about this. Right. If I say, okay, can you find the mean or max of this function L? So if you look at this function L here, what is the function L? L is a function of what? X, Y, and a lambda, right? L is a function of lambda, X, Y, and lambda. If you're going to find the mean and the max point, so what would you do? You basically, right, to find the mean or max or critical point, basically to find, let me just write, to find critical points. So what do? We set the gradient of L equal to 0, right? We set the gradient of L equal to 0. Gradient of L equal to 0, what does that give us? Exactly. So gradient of L equal to 0 meaning dl over what? dx needs to be 0, right? Needs to be 0. And dl over dx, what does that give you? dl over dx meaning df over dx plus lambda, then bracket side there, dg over dx equal to 0. Okay? And dl over dy needs to be 0, give you this. Okay? And the last dl over d lambda needs to be 0. But dl over d lambda, what does that give you? It gives you back the what? The constraint here, right? This is the constraint basically. You see, 1, 2, 3. That's exactly this 1, 2, 3 at here. Make sense? Right? So basically, original problem is constraint optimization. You want to minimize f of x, y, subject to what? To this g of x, y equal to c. And now, with the new definition of function Lagrangian in here, that constraint problem becomes what? An unconstrained problem here, right? Unconstrained. Okay? Yeah. Now, this is everything that we're going to look at. The optimal control is based on this concept at here. Okay? It's based on this concept. A simple concept. Of course, we're going to deal with much more complicated situation because our constraint is not going to be just one constraint. We have a dynamic system. Our constraint is going to be the system dynamics. So there's a vector, basically. You have state space equation, right? You have an n number of basically equations there, the n constraints. So I'll talk about it shortly. Okay. However, okay, just remember this concept at here, though. Okay, remember this concept. So let's take a look at an example. Okay, let's take an example, and we'll look at the details here. So let's say I have a function of this, and constraint is this. Okay, constraint this. And I want to find, or I want to minimize this function subject to this constraint. So now you probably say, why don't you say maximize this function here? Well, this function actually you can maximize that because in this case here, this function is basically the function as I was just drawing here. That's a paraboloid, okay, and minimum for this function is 0, okay. Minimum for this function is 0. If there's no constraint, minimum is 0 here, right? Yeah. And this constraint g of xy equal to xy equal to 3, and that's basically if this x-axis, this is y-axis, that's a parabola like this, okay, curve like this. So this is xy-axis. Then in a 3D, you have a curve here, and then you have another side, a curve over there, right? Curve here. So basically, walking along those curves, where will be the minimum points, okay, taking from this surface, okay? Yeah. So I'll show you the animation later, but let's do just the mathematical calculation based on the Lagrangian there, okay? Just the Lagrangian. So we define ourselves the Lagrangian fxy plus lambda g of xy minus c, okay? So which is what? X squared plus y squared lambda xy minus 3, like this, right? Yeah. Yeah.
What does that minus c?
C is a 3 here.
Yeah. Why we have that c? Is it possible to have just fx plus f lambda multiplying by g?
Yes, you could. If you move the 3 to basically, if you move the c to the other side, right? And then this is, if you call this is your g of xy. Yeah, yeah. Now, why do you have a c? Now, particularly in the future, you will see that my constraint maybe it's this. x dot equal to f of x of u and here. This is my constraint. Okay? Yeah. So not necessarily it's a simple constraint. This is a dynamic system basically. Huh? Yeah. Okay. So now what we do is we set this guy equal to 0. Okay. And that gives us 3 equations. So what do we have? First, partial everything over x. So that's 2x plus lambda y. Right? So practice partial derivative now. 2y plus lambda x equal to 0. And partial over lambda is xy equal to 3. Was that good? Yeah. Now solve the 3 equations here. All right, solve the 3 equations. So to solve this kind of 3 equations, let's say this is equation 1, and this is 2, and this is 3, like this. Right. So from number 1, so what do we have? Your lambda equal to negative 2x over y, right? 2x over y. Then substitute this guy here. Sub that into 2. Okay, sub that into 2. So what do we end up with? Sub that into 2. So that's 2y minus 2x squared over y equal to 0, right? Equal to 0. Okay, so simplify that. What do we end up with? We end up with x squared equal y squared, right? X squared equal to y squared. X squared equal to y squared. What does that mean? That means either x equal to y or x equal to negative y. Okay. So which one is appropriate? You look at basically your constraint, which is xy equal to 3. So which one do you think? Would you pick this one or this one? That's right, right? So this is not possible. So only x equal to y is possible. If x equal to y, then I'm going to sub that into 3, right? So we end up with an x squared equal to 3. So which means x equal to positive and negative root 3, right? Positive and negative root 3. If x equal to positive and negative root 3, which means when x is positive root 3, the y is root 3. When x is negative root 3, the y is negative root 3. So we have 2 critical points, right? We've got 2 critical points or 2 minimum points, basically. So at these 2 points, we have the minimum value. For which function? For this function f equal to x squared plus y squared. And what is the minimum value? Plug the root 3 here, root 3 here. The minimum value for the function is 6. Right? Yeah. So at this one here, function f of y, okay, has a minimum value, okay, x squared plus y squared equal to 6. Okay, so 6. So this is how you basically, in general, how you would approach this thing here. Okay, so if I gonna illustrate this situation at here, okay, so maybe I'll explain it a little bit at here first, and then we'll look at the illustration at here. So imagine this is the situation when you are walking along the curve. Basically, when you're walking along the curve, and then you will have certain points traced out along the surface here, right? here's another concept. Let's say if you are here, then you go up. Okay, this is the corresponding point on the surface. Is that all right? And then if you slice that surface, okay, just slice the surface, okay, with the z plane like this, then you end up with what? You basically end up with a so-called level curve, right? We don't have civil engineers here, but what's a level curve? You have this geometric, geometry of the land. And how do I describe the altitude of the curve? Basically, you slice all the land, right? And you have all different kind of contours. That's level curves, right? That's level curves. So if I'm here, you end up with a level curve here. If you're here, you end up with another level curve like this, right? If you're here, you're in another level curve. But imagine this, right? Where is the root 3? Basically, the root 3 is here, okay? It's here. At this location, you have a level curve. Okay, you have a level curve from the surface. Guess what? That level curve is going to be, well, first of all, when you slice this guy here, when you slice this one with a z equal to a curve constant, let's see if you slice that with z equal to constant d. This is actually end up with a level curve, which is what? A circle, right? A circle. So at the critical point, you end up with a circle actually is tangent to the constraint. Okay, tangent to the constraint. At the tangent to the constraint, meaning the two grading vector, remember the two grading vector, what a relationship? They are parallel to each other, right? At the same time, perpendicular. Whoa. That sounds very good. No, that's not good. Preparing to hibernate. So when is that gonna finish? But we don't. Okay, so let me show you the animation at here, okay? And let's watch what happens. So here's an animation I made in Maple. Okay, still working, yeah, okay. So this is basically the drawing I had it here. Let me explain what they are. Still working. This surface is the x squared plus y squared. Okay, that's a surface. And this circle is that x squared plus y squared equal to 6. Okay, so I just kind of pre-plotted the circle right here. And then this dot is going to be the dot walking along the xy equal to 3. All right? Yeah. The red color and the blue color are the grading vectors for the constraint, the g function, and the surface f function. I believe this blue color is the grading vector for the f of xy. The red color is the grading vector for g of xy equal to xy. Okay? Yeah. So just look at what happens when you started to walk here. So this circle, right? So basically, you see this circle here corresponding to that. Basically, when you are here, and that's where it is on that surface there, right? And you have a level curve, okay, at that location. So when you're moving until where? Until right here. What is that? That's basically the minimum location here. So this one maybe not as good as the next one here. Let me just kind of show you this one here. So this one here is gonna trace out the history of this dot on the surface. All right. So just watch the history of this there. Just enlarge that a little bit. So that's what you see when it's moving on the surface. And here is basically not a parabola, okay? This is kind of inclined curve, not a curve in a flat plane though, right? Because the motion at here is a curve at here. But in any way, you will see that where's the minimum point? Minimum point, it's at this bottom here, right? At the bottom there, all right? And that's basically I think there's a little problem here. This is not, why this is not tangent to this circle? That's supposed to be tangent here. Maybe I have some errors here, but this is a tangent. You see that, right? That dots end up with at this circle here. Why that dot is not in of that circle there? But anyhow, you get the gist of that, right? Yeah. Okay. Yeah. So here's another one here, and this is actually a similar one's approach as that one here. So this is a slightly different example here. Basically, you have the same surface. Let me just see if it's the same surface or not. Yeah, you have the same surface, x squared plus y squared. Now this time, we're gonna basically starting here walking along a straight line, okay? Basically, instead of walking along the curve xy, walking along the straight line here. So this is more of the drawing I showed you there. As you're walking along the straight line here, and that's what's traced out, right, on the curve, on the surface, which is the parabola. As you can see, the minimum location, which is right here, right, it's right here. At the minimum location, the constraint is tangent to what? To the level curve at that minimum location. Okay? Yeah. So, in essence, right, when we do the constraint optimal control, basically this is the number one here, right? That's what needs to be satisfied. Behind this expression in here, behind this expression, it's our the geometrical meaning is the level curve of that function f at that critical location will become tangent to the constraint g of x, y. That makes sense? Yeah. Okay. So, excuse me. After all of this in here, so now let's just try to tie it up with the kind of a system we're dealing with. Okay. What we're dealing with is, let's make a simple case study here. Okay. What we're dealing with is a dynamic system. Basically, x dot equal to f there. But in this case, let's consider a simple case is this. Suppose that you're going to let's say minimize a q x of u, okay, equal to 0. So let's consider the situation as this. So let's say u is the input. Basically, that's the input to the system, right? Okay, that's kind of the the system we have been always dealing with. We always have an input, we always have the output here, right? And x, let's say, is certain kind of states, okay, of system variables. And subject to a function, let's say, and f of x u, okay, equal to 0, okay, equal to 0. So for this one here, it might be just simply a certain kind of a function, basically. Sorry, actually I was no, there's a mixed up here. So this is the this u at here. This is our system. Let's see, right? U is input, and this one here is the this one here. Not minimize this guy to 0. Just minimize this function here. Maybe this is just simply 1/2 u squared, for example, right? 1/2 u squared. So if it's 1/2 u squared, if u is the input, so basically what we're trying to minimize what? Is the control effort, right? The control effort. So you're trying to minimize our energy, basically. Okay? Yeah. And if you plus another one, 1/2 x squared. Okay? This is scattered here. So instead of just minimizing the energy, you're also trying to minimize what? The value of x, right? The value of x. And that's actually one of the objectives when you do pole placement regulator. You're minimizing, basically, you're trying to basically bring the x back to 0, right? Bring back to 0. So that's kind of a minimizing problem too, right? But it just you didn't realize that. So and then if we do as we did, we define ourselves a Lagrangian function, so that L will become Q, okay, xu plus lambda, okay, f of xu, like this, right? Like this. Okay, then you basically set del L equal to 0, and just find the minimum point or optimal points. Okay. Now, what if we have multiple constraints? Okay, multiple constraints. Okay, multiple constraints. What does that mean? That basically means I probably have, instead of just one constraint, I have f1 at here, f2 at here. Actually, I use a g, right? But anyway, I think you know what I'm saying here. So maybe up to fn. Okay, maybe up to fn. So there are multiple constraints here. If this is the case, you actually do the same approach. So lambda 1, f1, lambda 2, f2, up to lambda n and fn. Okay, and n fn. So this writing is not that good. Let's define a lambda vector, which is lambda 1, lambda n. And let's define a f function vector, which is f1 up to fn, column vectors. Okay? Yeah. So what does this Lagrangian function become now in terms of the new definition? How would you?
Not the transpose type F2?
Exactly.
Or
Okay, it'll be this now, right? It'll be this. Okay, yeah. So bear in mind this notation in here. Okay, this notation. This is actually kind of the notation that you will see in the next lecture. Okay, when we're dealing with multiple constraints, and you have this writing here now. Okay. Okay, so I think I'll stop it here. Any questions? And in the next lecture, we'll go over even a little bit more mathematics. Okay. So just be prepared. A little warning as to the way of the writing here. A lot of writings though. It could be very boring. So.